Hello, good morning. Okay, okay, good. So the sound is good. You can hear me well. Is it good? Okay, I think that maybe my camera. Okay. Okay, good. So the last session we have been disconnected. So I sent an email. I don't know if you received the email or not. Did you receive the email? Because I explained that. Okay, so I will just check the mailing list because there is some configurations in order to send you to be able to send you emails. Anyway, you can. Okay, so I will check my configuration. But what I can tell you is that you can use your email to send me an email to my. I gave you my email address yesterday, first session, right? So you have my email address. So feel free to ask me questions and give me feedback or comments. Okay? Do you want me to? So my email address. I will write it now. Okay, so this is my email address. So just before starting the second session, just maybe some very brief recall of some of free space loss. So I think that you have all what you want, right? You have the slides for module 1, 2, and the physics, and okay. So you have all documents are available through the e-learning platform. Okay, so the free space loss is the electromagnetic waves naturally loses energy when they travel. So this loss is proportional to the distance. So the longer is the distance, the amount of energy lost is big too. So it's proportional to the distance and inversely proportional to the square of the wavelength. So it's very important to have this in mind, because when you send an electromagnetic wave, you know that if you increase the distance, you will lose energy, and it depends on the frequency and the wavelength of the electromagnetic wave. So this is the formula. If we know that lambda is the wavelength and it's equal to c divided by f. C is the light velocity and f is the frequency. So I just replaced lambda by the frequency and the celebrity of the speed of light, the distance, and if I use the logarithm formulas, so I have this. C is constant because it's 3.10 power 8 meter per second, and you have the distance and the frequency. So you have these variables and you have this constant, which I can calculate, and this is, I denoted it K, and K is equal to 147.5. Okay, so it's easy to calculate the free space loss for electromagnetic waves. The specific absorption rate is very important because this parameter is regulated by laws, by standards, and so on. Because you expose the humans to the power of electromagnetic waves, you have to be aware about the amount you are sending. So the human body is exposed to radio frequency radiation absorbs so the power from is absorbed from the radio frequency waves. Safety regulations determine the guidelines for human exposure. So the specific absorption rate measures, and here I want to, let me use the pointer and maybe I can, the unity here, the unit of specific absorption rate is watt per kilogram, since it is the exposure to a power. So it's very important to know this parameter because it is regulated and it is subject it is to standards and laws. So C is the conductivity of the body in Siemens per meter. E is the electric field in volt per meter, and D is the density of the body. So it could be animal or human, but it's organic body. So this is the formula. Specific absorption rate equals to the conductivity multiplied by the square of the electric field divided by the density of the body. Very important. The unit is watt per kilogram. Okay, very important. Read range. The read range is the distance you can read. You can communicate information, for example, between tag and antenna, reader antenna. So this read range, which is in meter, is the read range is directly proportional to the square of power, and alpha is constant. So it's very easy. It's just to tell you that the read range is proportional to the root square of the power. So, and we have concluded. Okay, this is just some before disconnection, and today I will be sure that I will finish before 200 minutes. Okay, so after that, so what we'll do today is to just do some applications, physics applications. Then we will try our your knowledge for module 1 by doing a quiz. It's a formative quiz. It's not mandatory or not taken into consideration for your evaluation. So it's just for you to see and to have an idea about how it works. So let's do the exercise. So the first exercise is to be familiar with the decibel and voltage and so on. So how will the ratio of electric power be expressed in decibels in terms of the ratio of voltage? So very easy, just to have in mind that the relationship between voltage and power is the resistance. So you know that the power is equal to the square of voltage divided by the impedance or resistance. So having this in mind, so if having this in mind, so if you have this formula, so it's easy to determine the dB. This is linear. So if you have here you have volt, and here you have watt, here you have ohm. So P in dBs, it's 10 log P1 divided by P2 if you have a ratio of 2 powers, because dB is a relative quantity, and usually we have ratio. If you have ratio of power, So it's easy. It's 10 logarithm P1 divided by P2, which is the ratio of powers. It's 10 logarithm power, okay? When you replace the power, you will have this ratio and you have the square of voltage. This is why if you use voltage, you have 20. If you use voltage. But if you are using powers, it's 10. This is why I gave you this exercise in order to be sure about the difference. Right, Jigjiga? Is it right for you? So if we use the powers, it's 10, logarithm in base 10, and this is the relationship. This is why this is equivalent. So 20 logarithm if we use amplitude, if we use voltage, but if we are using power, it's 10. This is the relationship. It's only applying the logarithm formula. Right? So, very easy. Is it okay for this? Okay. Now, we spoke about the antenna size. For example, we have a cell phone working at 900 megahertz as working frequency. So, what is the size of the corresponding antenna? So, this is very easy to calculate. So you use the formula of frequency and lambda because you have to determine the lambda, the wavelength of the working frequency, and after determining this wavelength, then you can determine the size of the antenna, because usually the size of antenna is lambda divided by 4. But usually when we ask you to design the antenna, we give you the relationship between the size and the wavelength. Okay, so for this case, we assume that it's lambda divided by 4, it's quarter of lambda. So if we calculate lambda, we have this calculation only by using the formula of C divided by lambda. So we determine lambda. Lambda is equal to 0.333 meter. So the length of the antenna, the size of antenna, is approximately 8 centimeter. Okay. So we have also discussed the beam width. Remember the beam width. The beam width, I told you that the beam width, I told you that it corresponds to the point, to the angle of the half power of the power sent by the antenna. But if you see the diagram, the radiation, the pattern, so you have the field of electromagnetic field, the antenna is here. So the beam width, very important parameter, because when you will design an RFID network, you have to choose the antenna, and the antenna one, yes, no, not between the two lobes most. No, this is you take the main lobe, only the main lobe, okay, and then you take this point and this point, and then you calculate the angle. But it is provided then by the buyer. Yes, it is provided when you buy the antenna. You have this information. You do not calculate it manually. Okay, so this angle, but you have to understand it. This angle gives you an idea about the directivity of the antenna. If it is narrow, it means it's very directive, and you have a lot of power in one direction. And if the theta is big, it means that you will be close to the isotropic antenna. because the maximum of theta is 360, so it's circle. But if you have a narrow theta, it means you are directly. So what I'm asking you in the exercise is to show that minus 3 dB from the power here is equivalent to the half of power when we are using amplitude or voltage. Okay, because here is power, so it is minus 3 dB. Okay, so very easy. Remember, when you are using the logarithmic scale with logarithm and the linear scale of the power. So we assume that we are searching about the half power of the maximum lobe. So the half power is P1. P1 is the half power of P2, which is the maximum of the lobe. So if I take 10 logarithm base 10 of P1 divided by P2, we have 10 logarithm half here. So because we have this, and then it is exactly minus 3 dB. If you take your calculator and then you use logarithm base 10 and you have this, so you have minus 3 dB. So when I tell you minus 3 dB, just remember, in the linear scale it's equivalent to, okay, it's equivalent to the half of the power in the linear scale. Very important. Okay, very easy too. So this is the, okay, now you have the ERP of an antenna system is 0.1 megawatt and the antenna gain is 7 dB. How much total power does the antenna transmit? Remember, ERP is also a very important parameter, very important. The ERP is effective radiated power. It is regulated. So when you have ISO standard and norms and laws, and you will be called to install an RFID network in a company, you have to be sure about the effective radiated power because it is regulated too. So the ERP is defined by the power transmitted by the antenna multiplied by the gain of antenna. So, and the unit of ERP is because EEG, which is the gain, it's without unit. So PT is in watt, so ERP is in watt unit. It's a power. So, but we told you that power, PT, is equal to the original power sent by the reader, and we reduce the cable loss because we connect the antenna to the reader by using the cable, and we know that by using cable we lose power. So the real power, or the true power, the true value of the power is PT, which is used by the antenna. So ERP is PTAG. This is the formula. So what I am asking to do is, we know that the ERP is 0.1 megawatt. Megawatt, it means that it's 10 power 6, right? So, and 7 dB. We have to convert this to linear scale and then to determine the total power sent by the antenna. Okay, very easy. So the ERP, the formula is here, but we know that EG, it is 7 dB. To convert this, it is in reality 10 logarithm EG. We have to find EG in linear scale, this quantity. So we divided 7 divided by 10. This is equal to logarithm in base 10 of EG. And then 7 divided by 10, it's equal to 0.7. And then if I I want to have this quantity because it is logarithm in base 10. So to calculate this, it is equal, we have to put here a power 10 power this quantity in order to remove the logarithm. It's not Neperian logarithm, okay? It's not base 2 logarithm, it's base 10. So for base 10, if you want to calculate this quantity, you have to put 10, 10, and then this will be removed because the 10 power is the reciprocal function of logarithm base 10. Okay, so this is why we have this quantity. And then we use the formula. So this quantity, if you calculate it, gives you 5. And then I will calculate PT by having ERP divided by 10. 0.1 megawatt, it's 100 kilowatt, and 100 kilowatt divided by 5 gives you 20 kilowatt. Okay with you? Very easy, it's not very complicated calculus, okay? So just you have all documents and just think about this. Okay, fifth point, the free space loss on DV for a 950 megahertz signal at 1 kilometer from the transmitter. So I have to calculate the free space loss, what I'm losing as energy if I have these conditions. Okay, very easy to do. So I use the formula I show you earlier. So your free space loss is equal to K, which is the constant including the speed of the light, and yes, and you have, here is the distance, and then here's the frequency. Maybe I didn't use R in the formula, original formula. Okay. I use D, maybe, sure I use D. Yes, I use D. So sorry, I put R, but it's D. K, it includes the C and P and okay. So it's very easy to we have the distance 1 kilometer. We have the frequency 950 megahertz, and then we can calculate and we have this constant. So we can calculate the free space loss for this, which is 92.1 dB. So the last exercise, you are traveling with a radio that operates in the same frequency as an RFID system. You are in a country where the allowed maximum power emission is 0.5 watt. To avoid interference, you have to keep your radio 3 meters away from this device. Now you move to another country where the maximum power emitted by this RFID device is regulated to be 4 watt. So the regulations change from a country to another. So how far away will you have to keep your radio from this device to prevent interference, because you are changing the countries? So very easy, we use the relationship between the distance and the power, the last parameter we saw, and we know that P1 is 0.5 watt and P2 is 4 watt. We know that we have the distance. So by changing the country, I'm seeking for the second distance to put away the reader in order to avoid interferences. So the relationship here is alpha. So maybe I changed my notation, it's not good. So here it's D, Okay, and here it's alpha. Okay, I think we used alpha in the okay, so this formula. And then, so just dividing the two equations, and then we can determine the D2, because it's proportional, the alpha will disappear, and then you have this ratio, and then we can just find the second distance. Okay with you? So very easy exercise, but it's important to be sure about our concepts, our parameters, our units, and so on. Any question? So now we officially, if an RFID, is it necessary to have from regulation? Yes. Yes, yes, you have to be licensed, especially when you have where you will use frequencies that are regulated. So this will be the subject of our second session today. So not all RFID systems, but for the most important ones, it's important to have license from regulation authority. Okay, and to respect this regulation, to have license. So okay, so I think that if you have question about physics, you can send me an email, and it's very easy. You can search the internet and find everything you want. But what I gave you in module 1, it's very important to know for your exam. Okay, for your final test, it is important to know all of this. Not complicated. Okay, so in order to see if you understood all the concepts, let's start doing the quiz. I will let you, but I'm sure that you will not see your notes. Okay, so keep your notes away, keep your document away, and try to do it before just saying nothing. I will let you. No, don't send me nothing. Just the only thing you can send is the summary of the lecture. Okay, but this is up to you. You have to do it as professional. So keep your documents away now, right now, and then try to do it, and then we will do the correction before starting module 2. Okay, just because I think this is available for you, I will go to the e-learning platform and I will make available the quiz. Okay, let me do this. So download the quiz and do it. You have 15 minutes. And you have the correction of the physics too. I made it available. Okay, correction of physics and the quiz correction. The quiz. Just confirm. Did you have? Can you upload download? No, just you have a pen, and you just do the quiz, and after we will discuss together, I will ask you, and you will if you want, I will be interested to know your score. So send me your score by email, just to know which score you obtained. I'm confident that you will not see your documents. I'm sure, because it's for you. Okay, it's not for me. So just be sure. If you have 20 on 20, it's correct. If you have 10, it means that you have to read your content. And okay, so it's not very complicated. So please I give you the top starting. So between 10 and 15 minutes. So you choose one correct answer for each question. Is it okay with you? Guys, is it okay? No problem? Okay, so start. Okay, begin. Do the... Just send me your score, final score, but keep away your documents, okay? Just do it as you are in a certification exam for CompTIA organization, because this is the same questions. The quiz of tomorrow will be more complicated. This one is simple. It's very easy. So tomorrow we will have a quiz for the content of today. Okay, 10 minutes, huh? So 30 seconds for each answer. One correct answer. Yes, so just read and then put write the answer. So you cannot click, or just read and Okay, yes. Is it a problem, Sayed? Is it for you? I think you can just, okay, good. Please, when you finish the quiz, just tell us that you finished in order to see how much time it will take to you to answer. Is it difficult? No. Okay. Yes. No official certification exam. You have 70 questions and you have to answer them within 90 minutes. And you have to reach 75% to succeed. Okay, so 70 questions, 90 minutes, and 75% to be certified. Some questions could be complicated, but we can see this tomorrow and in the last session too. We will have 2 other quizzes that are okay. That one. Okay, so it takes done. Okay. Okay, do. Okay, maybe 2 minutes more. One minute remaining. So if you want, I will give you the organization which can. I think in France it is possible to do the official exam for certification. I mean, not our exam. I'll just give you here the. It's almost was 70 questions. This is, but yes, Herzog, you can have it. You can, maybe many companies could or provide the test. They could, they can, maybe an agreement with CompTIA is possible with this company, so it's possible. So just the name of the test is CompTIA RFID Plus. Okay, now let's answer together. Which of the following tags do not have a battery? Easy. So give me the answer. Just type the answer. Yes, easy, passive tag. Okay. So which of the following tag types may have the largest data capacity? For 2, the correct answer is for the 2. Which of the following tag types may have the largest memory or data capacity? A, yes, A, active. Active. Second is semi-passive, but active is the correct answer. A. So the EIDC stands for Automatic Identification Data Capture. A, 2. Okay. So for the 4th question, a battery can be used as a power source in all of the following devices except. So here, why I give it, this is an easy question, but in the certification exam, usually we use except. So you have to find the false answer. So semi-passive, you have battery, you have a power source. Handle the reader, you have power source. Class 3, you have a power source. Okay, so this is C. Okay, C. Class 3, it's semi-passive. Semi-passive, you have power source. Yes. 4 is C. Okay, 5. RFID equipment test should be before. This is a common sense, huh? So it's should be performed before and after the, yes, D. Common sense. 6. B, right. Yes, B. It's the size of EPC code, 96 bits. Okay, not the memory. This is the memory, Herzog. Memory of the user memory. So match the following, column 1 and 2. So active, A, 5, B, 2, 1, and 3. No. What are you missed one. You have A5, it's correct. E5. B1 and 2, it's correct. And C3. Okay, what about C3? Yes. No. Yes. Yes, I mean, yes. B, it's 1, 2, and 3. Okay, just see your figure, and so B, passive, is class 0, 1, and 2. Okay, 0, 1, and 2. This is class 1, class 0, class 1, and class 2, passive tags. Class 3, semi-passive, and class 4, active. Okay? Class 3 is semi-passive because we start with 0. Class 3 is semi-passive. So C is 4. C is 4. Okay. Yes. Okay. The electromagnetic polarization follows the orientation of which of these waves? No, I told this verbally. Yeah, no. Yes, exactly. Yes, A. So the polarization, even if we have the two waves, we have electric and magnetic, the polarization is related to the electric wave, electric field. Okay? So if it is vertical, it's vertical, it's horizontal, horizontal, it's spherical, spherical, it's electric. So let me, maybe I was not clear about that, but just, I'm sure about that okay. So just here, electromagnetic waves, electric field E, and okay, linear polarization. If the direction of E, and circular polarization if the E direction, so field, electric field. So we have the reference is the electric field. Okay, maybe I was not so clear about that. So here it is A. Is it okay with you guys? Is it okay? Okay. So 9 question. A radio frequency signal travel fastest through. It's obvious. B. Yes, obvious. B. 10. All the following are true about semi-passive task except what? Good, Lisa. Yes. Class 1 is passive. It's not semi-passive. So there is only one which is false. It is C. So 11. Which of the following is not true statement about RFID? Which is not true. So which is not true. Not true. I mean, yes. Yes, sorry. Yes, it requires line of sight. The barcode requires line of sight, but not. So all others are okay with RFID. So 12. Specific absorption rate is linearly proportional to the electric field, directly proportional to the square of the electric field, inversely proportional to the electric field, inversely proportional to the square of electric field. These are no. You have to show your formula or to remember your formula. Yes, B, yes. Directly proportional to the square of electric field. Just to take a look. Specific absorption rate, which is important. So it is directly proportional to the square. So it's very important. If you have a very huge quantity of electric field, it's not good for humans. Okay, because it's proportional to the square of, proportional directly to the square of electric field. Okay, 13. The ERP parameter is measured in which of the following units? Yes. Yes, what? So it's B. B, I told you this morning. Okay. So just read your documents and notes. A perfectly omnidirectional antenna is called also A. Yes. Isotropic antenna. The three-dimensional area of electromagnetic field that is created by the antenna is called The three-dimensional area of electromagnetic field that is created by the antenna is called yes, Watara, yes, the radiation pattern. Remember this, very important. The three-dimensional area of electromagnetic field that is created by the antenna is called the radiation pattern. Okay? The beam width of an antenna is defined as follows. So, for here, everybody answers A. It's correct. A, it's angle between the two half power points of the main lobe. Okay, we explained this morning. Refraction of an electromagnetic wave refers to abrupt change of electromagnetic wave direction to return back, sum of the electromagnetic wave energy that is absorbed by an object, a change of direction of electromagnetic wave without returning back, a unidirectional traveling of the I have C and E. So the correct, yes, C is the correct answer, yes. So the refraction we haven't returned back. Okay, so remember. Refraction is here. So this is reflection, and the refraction is it. Absorption is in red. Brown is, even brown and gray is refraction. So the wave does not return back. Okay, voltage standing wave ratio is calculated by considering the following. So for this, yes, Herzog and Jigjiga, yes, D. We use the two interferences to calculate the VSWR. Okay, so D for that. In the electromagnetic wave, the E and B. Maybe sometimes I use B and sometimes I use H. So it's correct for the two, but so I can use H too. So in some reference we use B and H. So, but for magnetic field. So here, which is the correct answer? In the electromagnetic wave, the E and B fields should be parallel, should be perpendicular. Okay. Yes, B. B is the correct answer. And the latest. The lowest is the wavelength, the highest is the energy of the EM. The lowest is the energy of the EM. The biggest is the antenna size. The lowest is its frequency. So for 20, which is the correct answer? Yes, good. A. Remember the microwave. Microwave, it means that the wave in micrometer, very small. Microwave is highest energy. Okay, so the highest is in the lowest, yes, higher frequency. But high frequency is, you haven't it. You haven't highest frequency here. The only one is here, this. So for the energy. It corresponds to high Yes, yes, Mustafa. High frequency is high energy too. But it's inverse to the wavelength. Okay, so did someone obtain 20 on 20? Tell the truth, huh? Maybe, okay. Okay, 17 is good. Okay, 5, still good, 5. Good, 4 is good. Okay, if you have more than 5, it's not good. More than 5, it's not good. Okay, tomorrow will be tough, more tough than today. So just be be focused in the course of today. Okay, and for your final exam, I will pick up some of these questions. Okay, for your final exam with the Professor Naitali. In your final exam, you will have 50 questions. 50 questions. Okay. Maybe 1 hour for the exam. Yes, multiple choice question. Yes. Yes. Yes, Lisa, do you have question? I don't know, Mohammed. 50 for 60. In the official test, you have 70 for 90. Because depending, the question could be long. Maybe, but this is easy. I gave you just very easy questions. So if you have question, if you have 1 minute to read, to answer, to choose, yes. Yes, for the summary of lecture, just send me 1 pager. It's a summary of the first lecture. You can send it next week, or you have 2 weeks after. No, not. It's not mandatory to send them after each session. So I will let you to. So yes, it's a very important question. 2 weeks. So I have 2 weeks from the end of for the 3 lectures. 1 page summary, yes. You have to read, and I want in the summary the most important things, and with your own words. Okay, it's important to have your own words, not copy and paste. Synthesis, scientific synthesis. Yes, 3. I will give you the second one today. Okay, maybe in the end of the session, no, 3 lecture. Yeah, we have 3 lectures, we have 3 courses, but you have to do 3 duties. Okay? So for the first session, I didn't give a summary to do. I called it lecture, but we have 4 lectures, yes. Okay, so maybe for this technical question, we can answer them at the end of the course, because I'm aware about time. There is no summary. No, I gave you a so just maybe the lecture. Let me download from the library what is the lecture. The first one this one. This is this one. This is a paper, okay, from IEEE Potentials, speaking about RFID help for new technology or threat of privacy and civil liberties. So you have to read this paper and to do a summary of that with your own words and to send me the summary. And this is what I called lecture. This is a complementary knowledge for you. It's related to the RFID, but it's complementary knowledge. For you, it's very important to read in English and to make a summary in English. This is you who will do the summary, Lisa. Is it okay with you? So the first one, yes, this is on the platform. Yes, and this is what I mean lecture. Lecture the lecture is done by you in order to, this is a complementary lecture. Okay, so the first one is here, the second one I will give it to you today. Okay, so you have to read this carefully, you have to have your opinion about that, like a criticism. You have to do a very good job by doing analysis of this paper. I do not require just copy and paste some part of this. No, it's a long paper and it's challenging to summarize this in one page and to give your criticism and your analysis of this. Okay, this is why I let you to do it within two weeks, because it's not easy to do that. Okay, and this can be used if you have problem with your final exam. We will see your performance in summarization and analysis and critical analysis. Okay with you guys. So I will give you the paper for the second lecture today. It will be on the platform. All the lectures, the three, and you have the summary of the course. You can see the title of your... Okay, good. So now let's start the second lecture or module. Okay. But it's the lecture for in the classroom. So the outline of the second course is this. So we will recall some concepts about the network, RFID network, the frequencies, the warehouse management, the tags, the readers, the antenna, the possible configuration, constructs, and so on. Okay. So remember, the general configuration of RFID network is composed of tags, and you have exchange and of information with the reader through the antenna, and then you have a network, and then you have a middleware or a host computer, you have a database. Okay. Maybe it's big. Okay. Just this, it will be the right size. Okay, this is we saw this last course. Okay, the frequency allocation, it's very important here. Very important. So remember, in your quiz, you will have a question about that. Jigiga, yes, what do you mean? Do you mean that I will reduce this one? This is better? This one is better, or this one? Is it good for, okay, is it good for okay, Jigjiga, is it good for you, this format? Okay, good. So the RFID frequency allocation is very important, very, very important. So, and you have to remember that, if you can, all what is in this slide is very important. So there is low frequency RFID, high frequency RFID, UHF RFID, and microwave RFID. Remember, we have seen the spectrum, the frequency, the spectrum frequency, and there is four RFID technologies, depending on the frequency of use. So if we use applications in low frequencies, we speak about low frequency RFID, then high frequency RFID, UHF RFID, and microwave RFID. So in low frequency RFID, the frequency used are 120 till 134 kilohertz. This is for low frequency allocation for RFID. And the ISO is the International Standard Organization, and this is the normalization, the standard. So the low frequency RFID is regulated by the ISO 11784 and 5 and ISO 14223. Okay, so what is important to remember is this: it's the frequency, the range of frequency. So 120 to 134 kilohertz is the low frequency RFID. We will see the application of that. And then you have the high frequency. You have RFID, which is working in high frequency. There is only one, it is 13.56 megahertz. Okay, so you increase the frequency. And then the EPC global, the widely used, the most widely used is the UHF, ultra high frequency, and the frequency is within the range of 850 and 960 megahertz. So for Europe is 865 until 868 megahertz. So in France it is mainly this. You are not allowed to use UHF RFID beyond this range. For US, for example, and Canada, this is this range. So it's not the same frequency range depending on the country you are. I will give you some example of for countries. And then you have, for active RFID, you have the mainly active. You have the microwave RFID, microwave frequency allocation. It could be from 2 gigahertz until 10 gigahertz. Okay, so you have to remember the 4 technologies for RFID, the 4 frequencies range, frequency range. Okay. So now let's begin by the low frequency RFID. The RFID working in 120 and 134. Okay, so the exact frequency is 125 and 134 kilohertz. Okay, this frequency is free. Remember, Mustafa, I think, asked us a question about if it is mandatory to have a license from an authority to install an RFID. For this technology, for this low frequency RFID, it's not necessary because the frequency is free of use. Okay, within the world, it's worldwide, so you can use it in any country you want. Okay, without restriction. But it's very restricted because this low frequency RFID, it is what we called, I think that I used it here, near field technology. It's technology where the distance from the tag and the antenna, it's not very big. So we can see the applications. The main advantage of this RFID, low frequency RFID, is that it can penetrate most materials, including water and tissues of the body, which makes it animal-human identification. So there is no problem to use this low frequency RFID 125 and 134 for humans and animals. But it's not inside the human or inside the animal. It's a ticket, it's a tag. So the tag, if you are using an object which is filled of water or tissue, it is better to use this technology. Why? Because this technology, this frequencies are not sensitive to the water, are not absorbed by the water. Okay, so remember the absorption. These frequencies are not absorbed by the water and the blood. When you are human, we are filled of 60%, not 70% or maybe 80% of water, because we have blood inside our body, exactly like animals. So for soldiers, for example, the American Department of Defense, when you use RFID to identify soldiers, the tag is this, because it's possible to read these tags without having the risk of absorption, because in this frequency are not absorbed by the human liquids, which is blood and water. But the inconvenience of these frequencies, they are sensitive to the electrical noise from the engine and industrial environments. Okay, so if you have an electrical network which is not good, not isolated, not grounded, so it could be a problem. But we can resolve it easily by make a good ground, mise à la terre, en français, mise à la terre, good grounding, and so it could be resolved. But this is the inconvenience, disadvantage of this technology, of these frequencies. The rate of data transfer is low because when when you decrease the frequency, of course you decrease the speed of transfer, the speed of exactly like if you have a PC, if you have the clock running with a high frequency, it means that your PC is fast. Or if you have 3 gigahertz or 4 gigahertz, but if you have 1 gigahertz, it means that your PC is very slow. So this is because this is the lowest frequency. It means that the data transfer is very low. So it will take 70 milliseconds to read command. This is normal. When the frequency decreases, the rate of
the data decreases. Okay, the tags are expensive. It's not cheap because we are using technology, a different technology for the reading. We will see the way to exchange information is different from other technologies because we are in low frequencies. Most of the low frequency system can read only one label. This is another inconvenient, another disadvantage, because we can read only one label and cannot bear simultaneous reading of several transponders. I will explain to you why. Because it's the same, why it's more expensive, why we can read only one label, why the data transfer is very low. I will explain to you. It's related to the technology, to the way the information is exchanged. And the read distance is very low. It's few centimeters, depending mainly on the size of the label. So you can tell me why it's a few centimeters. It's not useful. It could be useful for some application. So if you want to identify a body, remember the soldier usually have like a piece of metal to identify with their name, and if you have a tag like that, you can have a reader that you can take close to this tag, and then you can have all information. So it's not recommended to have this information read from far distance. So it's useful because if we want this information about a soldier, about a human, so we need near field. Near field, it means we have to be close to the person in order to read this information about it. Same for animals. Yes, exactly, Hassan. Yes, for payment solution. But payment solution and passports and so on, it's better to have them in high frequency. Okay, it's not very low like this, but high frequency it's more so, because here you have few centimeters, but for high frequency you have maybe 1 meter or 3 meter or 3 meters. It's maybe it's more useful. Yes, it's due to distance, but to the technology used, because when you are working in low frequencies, you cannot use the same technology like if you are in high frequencies. Remember the size of antennas, remember many things, because this is very low. But you can find a type of applications that are useful for this technology. As I told you, human identification, animal identification. You have cows and you have beefs, and you have I don't know if you see that, you have just a label in their neck, and then you can follow all the pedigree, all the information about the beef and so on. But you do not to read this 1 kilometer far from the beef. Okay, so when you want to access to this information, you just have to be close to this animal and use the near field communication, near field technology. Remember this. High frequency is increased compared with the low frequency. It's 13.5 megahertz. So the wave penetrates several materials. We have the same advantages like low frequency, because we are not the water and the metal are not obstacles for that. So you can, so the high frequency is not absorbed by the water, by the liquids, which is an advantage, because, and as you said, Hassan, it is used for the payment, because when you use this for the payment, you use a smart card or something like that. So you take this with your hand, and your hand there is a blood, and in the blood there is liquid, and liquid it's water, and water, if you use you use a technology that is absorbed, electromagnetic wave, which is absorbed by water, it's not good because you have the, okay, I will draw something. This is a man of human, okay, a hand of human. You have this smart card. You have RFID tag here. If you bring this card with your hand, you have water here, blood. Except if you are alien, you have blood. Okay, blood. Blood is liquid, and we know that in that frequency, in the low frequency, it's not a problem for because if you have a reader here, okay, assume that you have a reader antenna, then you communicate, exchange. This is electromagnetic wave. You have blood here. If you have absorption here, up, there is no electromagnetic wave to come to. So you have to choose the right frequency, the frequency which is not absorbed by the material you are working with. Okay, so and for these two frequency, the 13.5 megahertz and 125 and 134, there is no problem working with water and methane. Okay, very important. This is why when you are tracking humans, animals, and organic bodies and so on, this is the two technologies that are used. Also for passport control, because the passport you bring it with your hand, huh? Okay, and you take it close to your body. So this is important to use it, and the HF technology used for passport control, for example. So the wave penetrates several materials. Penetrate, it means it's good. The labels can be incorporated into various non-metallic objects. It's not affected. So there is an additional advantage compared with low frequency. The technology is not sensitive to the electrical noise. Of course, the transfer rate is better, 20 milliseconds for a read command. Okay, the tag is cheaper than the low frequency, and you have more capacity. The reader can communicate with multiple transponders, another advantage compared with low frequency. So the read distance is about 1 meter, which is correct and useful for some application. Passport, for example, for the police, do not want to have someone just hijacking the passport information. So 1 meter is correct between the reader and the passport, for example. So the standard is ISO 15693 and 14443, and the very important standard to remember is this one. So this is the subject of our third lecture, classroom lecture, the standards. Okay, let's progress. The UHF, the most widely used technology. This is the biggest amount of applications. UHF, 860 is for Europe and 960 for US and Japan and so on. So the UHF, so we increase the frequency, and this frequency is somehow complicated because you have cell phones working on that frequency and so on. So the communication distance between tags and reader is longer, so you have more distance, up to 10 meters, which is very good, depending on the number of antennas and so on. But you have a poor performance in the presence of metal and liquids. Poor performance in the presence of metal and liquids. and the labels can be glued on into non-metallic objects. High transmission rate, so the rate is increased, and fast, and effective collision avoidance technique. This is somehow similar to the Wi-Fi. So the UHF tag are cheaper because we can print them and they are very small than that of high frequency, since their manufacturing process is simpler. Risk of interference, yes, because there is multiple applications and system operating in the 860, 960 megahertz, which we call the ISM, which industrial, scientific, and medical bands. So from today, you will be familiar with this. So I will repeat and repeat and repeat UHF, LF, and HF, and microwave. I will repeat this. So don't worry about you will be familiar with that. So the microwave RFID is between 2.4 until 10 gigahertz. It requires semi-active or active tags. The range is up to 200 meters and can reach 1 kilometer. ISM and ultra-wideband regulations, there is regulations. Very high transmission rate, the fastest transmission rate, with fast and effective collision avoidance technique. The standard is built for 2.45 gigahertz under the ISO this 8004. It's very important. Remember, the other ISO was 8003. Risk of interference, because here we have the VLAN and the WLAN and the Wi-Fi, because this frequency, and used in highway toll collection or vehicle fleet identification. This is what it is used in Dubai and London and Roissy Charles de Gaulle, to many applications. It's not free. It's not free, Mustafa. It's not free. Okay, it's not free. Okay, so if you are use this in a communication between businesses, you have to have a license for that. So it's better to have a license, because you cannot use this. If you have problem, you will because it's not free. If we compare low frequency reading distance less than 50 centimeters, why Wi-Fi is free? Because it is used inside, but if you are using RFID, usually it's to do business with others. It's not if you do business with others, you have to inform about that. Okay, and this is why. And we will see two configurations. One configuration is denoted by closed loop configuration and open loop configuration. If you are working in closed loop operations, it means that you are inside your building. It's correct. But if you are working with open loop requires to inform the authority. Okay, low frequency, less than 50 centimeter, high frequency, less than 3 meter, UHF, 10 meter, up to 10 meter, and over 10 meter. Advantage, not affected by water and metal for low frequency, no restriction for this frequency. Disadvantage, relatively expensive, electrical noise sensitivity, and low reading rate. So animal tracking, human identification. High frequency, not affected by water, metal, same. Read several tags simultaneously. Less efficient than the low frequency to penetrate metal and water, but it can do this. So access control passports. UHF range is longer, well standardized, high rate, easy to produce, cost is very low, high reading rate. But it is absorbed by water, reflected by metal. So the enemies of UHF are water and metal. The frequency interference with those of interferes with those of other application, industry and supply chain. Microwave, longest read range, very high rate transmission, expensive, relative short life because of batteries, absorbed by water, absorbed by metal, like UHF, used in surveillance, localization, toll collection. Okay, so now we can take 10 minutes break. Is it okay with you? Okay, 10 minutes break. Okay.
Sébastien va venir vers 1h. C'est pas Élie, c'est Sébastien comme logiciel.
Sébastien,
il va venir à 1h. C'est ça, c'est le soir.
Ok.
Ils sont d'une réunion, là, ils vont sortir avant de réunion. Oui. Ça, là, vous avez signé, mais c'était pour réclamer votre souper avant.
Non, oui, j'ai signé.
Ah, ouais, c'est ça. Je puisse le faire signer. Puis ça, c'est le nouveau prof en éducation. Le marque d'embauche. Le salaire, c'est marqué.
La bénéfice.
C'est le salaire pour le marque Jean-François Richard. Puis lui, c'est temps partiel, puis il est non syndiqué, il n'y a pas de bénéfices, il n'y a pas. C'est 5 mois. On l'embauche depuis le 1er décembre. Ils ne font pas le même calcul que comme on faisait, c'était pas 5/12e, puis il faut le nombre de crédits. Ils n'ont pas fait ça, lui a accepté ça. Ben, ils ont calculé, eux autres, divisé par 20 payes, fois 11 crédits.
Il fait combien de cours?
9 crédits. Plus, il est sur un comité. C'est ça qu'il a dit. Puis on a un email qui dit que lui accepte ce salaire. Mais c'est pas possible.
J'ai discuté avant.
Ah, avec moi?
Oui.
Ok.
Le calcul n'est pas comme on le fait d'habitude. Ouais, non. Puis... Linda, est-ce que tu peux fermer, s'il te plaît? Ok, donc... oh no, there is encore 3 minutes remaining. Okay, we can continue, can resume our course. So we can use RFID to perform warehouse management, and there is several and various applications that are possible depending on the company goals. So you can have the dog portal configuration in order to manage the shipping in and out for goods and items. So you have a portal configuration. You can use the RFID to perform inventory management. Okay, and you can use RFID to localize items and pallets inside the warehouse. So there is various. Now, what is a read zone? Read zone is very important. Read zone, when you have a network, you have antenna. You can have multiple antennas. So you have many antennas in your warehouse or in your space, and then each antenna send the electromagnetic waves. So you can have a second antenna here. You can have let me just show you. Maybe we can have an antenna here, and then we have another covering zone. So these antenna are connected to the same reader. Okay, and you have two antennas, and then you have this, and you have antenna, a third antenna. Usually you can connect 4 or 5 antennas to the same reader. Have this, and you can have this space covered. So the read zone, you have your tags here, you can have tags here, you can have, okay, so this will be the read zone. Okay, so this is this zone, and this zone, and this zone. You can have a shape of a space covered by the electromagnetic field. Okay, so okay. So the read zone is defined by the radiating antenna connected to the reader and the tag architecture. So this tag, because you can read this tag here, you can define the read zone where you can read your tags. The shape of the reading zone, which I tried to remove, is a 3D shape and depends on the orientation and the number of antennas, and the orientation of tags. So it's better to have tags here, of course. Okay, so this is the zone where you can read your tags. Okay, so to summarize the classification of RFID system, the RFID systems can be classified according to the 2 key parameters: the operating frequency, remember 100 to 25 kilohertz and 134 kilohertz; the high frequency 13.556 megahertz, the UHF 860 and 960 megahertz, and the microwave RFID 2.4 and 5.8 gigahertz. You have to remember these values. Okay. The tag powering, passive, active, semi-passive. So you know that. So just to recall and to summarize. Yes, for HF, yes, Watara? No, it's not a range. You have this, and you have another frequency rarely used. It is 400 megahertz, but this is only one. There is no range. Even here, you haven't range. Huh? If you are working on a network, you have to choose one frequency for your network. Well, I will show you the channels. Okay. There is no range here. It's 205 and 134. Okay, the passive tags, just to remember, to send its response, it should be activated by the reader, by the antenna reader. This type of tags use the energy it receives through the electromagnetic signal after a reader request to power the chip. Okay, there is two components in the passive tags. You have the inlay and the insert. Inlay, insert. The inlay is composed by the chip, the aluminum copper of the antenna, or silver, copper or silver or aluminum, the antenna, the chip, the antenna, the polyethylene phthalate PET, which is a plastic layer substrate on which we put the antenna. The IC are assembled together, okay? And this is the inlay. This is the inlay. So the inlay is the IC and the antenna. And then they can deliver by the label to the form of label, and the label could be dry or wet. Without adhesive, it is dry, and wet if you have adhesive, like a glue. Okay. The insert, you can insert your, the insert is the plastic box here. You can insert your inlay inside this in order to protect this. For example, to protect from absorption, if you are putting this on a place where you have liquids or metal. Okay. So the inlay is inserted between a label in the front and an adhesive to the back. The inserts are available in different sizes for different applications. It could be thick, like this, in plastic, or in paper. Okay, this is the inlay, and the insert is the paper. Inlay, insert in plastic, insert in paper. The active tags, two types, the active transponders and the beacons. Beacons come from beaconing. Beaconing, it means that they permanently transmit the signal. They are very helpful for geolocalization, for example, geolocation purposes. So the active tag includes an internal battery for the chip power that is used to transmit the response of the signal, just only to recall the active tags. So regular, which is called the active transponder, and the beacon. Beacon is transmitting continuously the signal. Semi-passive. Remember, you have sensors inside. Semi-passive tags use an internal battery in order to power sensors or other processors. The life cycle is up to 25 years. The read range is more longer than the passive tags, faster than the passive tags, cost more expensive because you have more stuff on the passive tags. And the application, asset management with condition monitoring. Condition monitoring means that you have to monitor, for example, humidity, temperature, and so on. The reader, interrogator's role and type. Provide the energy to the tag, define the operating frequency, read and write data to the tag, and communicate with the host computer. The types, you have handled readers. The reader, the antenna, and the application software are all parts of a single device. Remember, in the last course we had an image for that. So it's all is in one device. A vehicle mount or mobile, it's placed on trolleys or powered vehicle that you can move around, and the fixed reader are placed at locations where items must pass through, such as entry and exit points. Now the question about the frequency, channels, and so on. Okay. Let's focus on the UHF, which is the widely used technology, UHF RFID. if you take North America, for example, we said that the range is 902 to 928 megahertz. Okay, the power should be, the regulation in US should be 4 watt, considering the effective isotropic radiation power, EIRP. Remember, it's very important. It's why I told you this is very important to remember. So some countries use ERP, the effective radiated power for regulation, and others use EIRP. So the relationship between ERP is 1.6. So it means, if you see that, it means that in US you have to be below 4 watt EIRP, and the number of channels is 50. So this is what is allowed in US. So if you have readers, you have this band to work with, and there is the channels. You have 50 channels. Okay, 50 channels. So you can have a reader working in 906 megahertz, another reader working with 916 megahertz, another reader working on 926, and you can have a reader working at 902.5. This channel, it's 902 megahertz dot 5, 903, 903.5, 903.4, and so on until reaching 906. Okay, it's a step of 0.5 megahertz. Okay, this is why you have these channels available for your application in US, and you have to limit your power to 5 watt ERP. If you compare with Europe, France for example, so you have 866 to 868, there is very less number of channels, and you have to limit your power to 2 watt ERP, which is to have equivalence, you have to multiply this by 1.64 to have to compare. Okay, which is less than so more severe than North America. Okay, and you have the other example for the other countries. So just to remember that the gain of antenna, for example, this antenna, it's called dipole antenna, and the pattern diagram is, radiation pattern is like butterfly. If we compare with isotropic, and you have the gain of the antenna, the gain is this part. Okay, is it okay for you? This is very important to understand. So you have to remember Europe and North America working, the number of channel and the regulation related to power. Okay, is it good for UHF? Okay, okay, very important thing is to know is the exchanging information in an RFID system. How we can exchange information, how we can do the reading from the reader to the tag. So there is two methods, and you have to remember these two methods. The first one is inductive coupling. The inductive coupling is the animal human low frequency and high frequency. It uses inductive coupling. Inductive, it means that they use coil, the bobine, transformateur. Okay, for a transformer, you have two. So they use the magnetic field mainly to communicate. Okay, they use magnetic field. This is why it is a near field coupling. You have to be close. This is the reader, and this is the tag. Okay, the reader with the antenna. The antenna of the reader is here, and the antenna of the tag is here. So you have to be very close, few centimeters. This is why this technology, inductive coupling, because it is using magnetism, because it is using coils like a transformers, the exchange of energy, the exchange of information is done by the magnetic field. So this is why it's not sensitive to the absorption in liquid and metal. So because it's near field coupling. So the transponder, which is the tag, and the antenna of the reader are coupled by the magnetic flux through both coils. Okay, all the energy used in the tag is drawn from the primary coil of the antenna of the reader's antenna. Okay, so the first method is inductive coupling. The second method used by UHF and microwave RFID is the backscattering or backscatter coupling. The electromagnetic backscatter is similar to radars, the one used by the radars, because it's far field, so you can be far from the object, and the reader can be far from each other. Okay, so the antenna, the reader sends the signal to towards the object. The object will receive the signal, and then it backscatters the signal. Remember, in our course, we are using a natural evolution or traveling of the waves. Remember, we have refraction, reflection, diffraction, but we have scattering. Scattering, it means that the wave come to the object, and then the object reflect in many directions. Why it is important to have it in many in diverse directions and many directions? Because it is possible to read after that, even if we are in this position or in this position or in this position, we can have. If you have a pure reflection, it's not good, because you should be here to receive. You should be exactly here to receive. But in radars, you send and then you receive from everywhere. Scattering. This is the word scattering. So this is used in the communication of UHF and microwave RFID. It's a scattering, a type of reflection, multiple reflections. So you send the wave to the tag sends the response after modulation, after changing the wave, because the object should have to send the information inside this signal, and then the receiver, which is the reader, will receive through its antenna the information backscattered by the tag. Okay, very important. So in UHF and the microwave, the information is exchanged thanks to the backscatter coupling. The antenna reflects part of incoming electromagnetic wave back to the sender. Electromagnetic wave is reflected by objects that are larger than half of the wavelength, and the UHF facilitates the construction of antennas because the antenna are very small, so you can do this system. Okay, it is not possible to do that with this because the frequency are very low. So if the frequency we saw earlier that the size of antennas are related to the frequency. So if you have a low frequency, you have big antennas because and if you have high frequency, you can design a small antennas because it is inversely proportional to the lambda, to the wavelength. This is why it's possible to do backscattering in UHF and the microwave, but it is not possible to do backscattering in low frequency. This is why we use the other type of coupling, which is inductive. The only way to communicate is to use magnetic. We have electric and magnetic. For this low frequency, we use magnetic because the frequency are low. Okay, I have question. Scattering can speed on up process if we have many antennas. Yes, this is why we can have multiple reading. This is why it is faster than the inductive coupling. This explains. Yes, I told you earlier that we will see why. This is the reason why it's faster. It's multiple reading and so on because of the type of coupling. The coupling here is backscattering. These concepts are very important. Okay, and tomorrow you will have a question about that. So remember this. Is it okay? So inductive coupling, backscatter coupling. Inductive is for LF, RFID, HF, RFID, passport control, and so on. It's inductive coupling. UHF, warehouse management, and so on. Microwave, control of the cars flow, and so on. It's by backscatter coupling. I told you that I use B and H for the magnetic, so sorry, here is H. So this, just to recall that the E and H, the E and the magnetic and the electric are perpendicular. This is the direction of traveling, okay, of the wave. Very important. The polarization here is vertical because we have this, okay. So the UHF use electric, very important here, very important. So UHF system use the electric field to communicate. And the LF and HF use magnetic field. Okay, so it's obvious, it's logic. Why? Because we have backscattering and we have inductive coupling. Inductive coupling cannot use the electric field. Okay. Okay, guys, feel free to ask me questions. Huh? You have to obtain 20 on 20 questions tomorrow. Big challenge because the questions will be tough. Okay, the polarization. Yes, magnetic field. Yes, Hena, yes. Low frequency, because it is using the inductive coupling, it used the magnetic field. Okay. So now the polarization. Remember that I show you this picture. Okay, I show you this picture. Yesterday we have this antenna in our lab, and even in the shape of the antenna, I know that it's linear. This is linear antenna because it's like not spherical, not circular. So what it means, the linear polarization is the reading depends on the tag orientation of the antenna polarization. And remember that the polarization is linked to the electric field. Okay. So vertical polarization, electric field, direction of propagation, antenna, and horizontal polarization, the direction of propagation. It's not limited to RFID. Yeah? The polarization of antennas is everywhere. So when you are studying or buying antenna, yes, everywhere. This is a parameter of the antenna. Okay, there is no specific to RFID. This is radio frequency communications. Okay, circular polarization, it works this way. So you have changing right hand, and right hand, and you have left hand circular polarization. There is two subcategories. You have right hand and left hand. So circular polarization, the tags can be read independently of their position. Of course, with this it's very very directive, huh? But the position of tags is very important if you have to perform a good reading. If you use this type of polarization, you have to be very to work carefully. Why? Because the position of tags are very important here. Okay. Yes, I will give you an example about that. When you are using circular polarization, it doesn't matter where you can put your tags. Your tags can be read because you have a changing position of the field. So if you have your tag here or here or here, it doesn't matter. However, the range of reading, the distance of reading, of course, it's not possible to have a good. Here you have a very far possibility, directivity, but you can have long distance of reading. The read range is high. Here you ensure your reading. The reading is good, whatever the position of the tags, but the read range is smaller. So because you have almost 50% of the power which is lost compared with the linear antenna. So directivity, if you want to have in your application directivity and a long read range, use linear polarization. If you want to ensure the reading, you want to guarantee that you cannot miss any readings, use the circular, because circular you are sure that you will catch the tag, but the read range is smaller, and the shape of antenna here is like square, but it's close to circular. So this is why this antenna is circular. Okay. So yes, this is circular. Optimal orientation. This is should be smaller. The distance horizontal the best, even if it depends on application. Not really, Watara. Just let me explain to you. With this polarization, you can go far. You can have a long range, distance, read distance. Okay, because you focus your energy. You do not lose your energy. You are very directive. So your energy is very focused. Okay, it is in the same direction. It's focused. It's concentrated. But if you have this, your energy is lost because you do this rounding, this movement. Okay, so you cannot go far. So if you use linear, you can go far. You can read tag there is a long distance. For example, you have, if you know that your tag is here, okay, if your tag is here and you have your antenna here, you know that it is here, and same position, and it is fixed, and it is well defined, and so on. So sure that if you have many tags here that are far and they are all in the same position, so you can use horizontal, for example, because there is, for example, 5 meter, let it 6 meter. But if you have this configuration, you have a reader, you have tag here and tag this way, random position of the tag, and you have a tag at 6 meter here. So maybe with circular, let's put the same tags. Maybe with linear you miss that. You miss that here with the first configuration. With the second, because circular, you can catch everything, but you cannot have enough energy to reach this. Okay? This is the difference. So depending on your application, depending on the position of your tag, you can choose this or this. Okay? If you know a lot about your tags, you know that they are in the same position, they will not change the position, and you know the distance, and you know, so use the maximum of power by linear polarization. So this is possible. But if you do not know anything about your tags, so maybe it's more secure to use circular. And usually in many applications we combine the two. We do a mix of linear and yes, no, not in the same device. We can use what we use in our lab. For example, we use one circular and one linear, and two linear, one vertical, and one. So we can ensure we have the distance, we have, so you can have 3 antennas. Sure, it will cost more, it will cost you more, but you guarantee your reading. You have the test, you do the test, and you know the best polarization. Okay. Okay, so optimal orientation. So if you assume that you have this tags, you have this antenna. So if you are using the circular polarization, by using the circular polarization, the best tag, the best rate can be reached by A and B, because this is circular. You can cover this distance when you are reading, so you can reach the chip and then you can collect the information. This less efficient. It is possible with circular polarization if you have this position, but with this position we cannot reach the chip easily, so it's not recommended. This is not recommended, this position of the tags. So but if you have information about the position of your tags, you can do a right reading, but if you do not, you can combine. This is just an example. Between tags, it's important to respect some distance, minimum distance between the inlays. This is the inlay, and the white is the insert. The inlay, so the distance, the minimal distance when you have these tags is 12 millimeter. Even if you respect, if you do not respect these conditions, you can have interference and a bad reading of the information into the chip. So if in this position the minimum is 12, and in this position the minimum is 25 millimeters. If you have this here, it's not good, because you will have interferences and it's not good. If you have this more closer, it's not good, because you do not respect the condition to have this distance. Okay. And usually when you have, we can have a reflection. Remember that this will be good because this will reinforce, will give more energy because of the reflection for reading this. But sometimes if we have destructive interferences, it's not good, because if you have opposite and destructive interferences, you can lose the signal. This is why you have to perform tests in order to see if you have multiple reflections or not. So we have done this type of experiments in our lab, and we put RFID tags here, so away from different distances, and we perform reading with the antenna here and the reader. And we put its UHF RFID, and we have a metallic support here, and we will perform multiple reading in order to see how it reacts. So the RFID tag near a metallic object could not be detected because of the electromagnetic wave is reflected by methods. I speak about UHF and microwave. So to highlight the effect of the metals on the rate of successful readings, we proceed as follows. We put 6 RFID tags near a metal plate, and then distance from 0 millimeter to 10 millimeter, and we perform 500 readings. So, and then we count the number of successful readings for each level, and we repeat 10 times this experience in order to have an average. And the results, when we are using the metal to assess the metal effect, are as follows. So to ensure the successful reading, if you have the gap from 0 to 4 millimeters, we are not in 100% readings, success of readings. So when the distance is 0, in all cases we have 0 successful reading, no readings, because if you have metal, you have UHF or microwave RFID, it's not possible to, because we have reflection, absorption, and so on, we cannot have the correct reading for this. We start to have good readings after 4 millimeters. After 4 millimeters. After 6, you are safe. So what we can do, we can insert this in plastic in order to isolate it from the metal. This is the solution. So if you are 2 millimeters, it's not correct. 3 millimeters is not correct. 4, it's not correct. Beyond 6, it will be good. This is just to give you an idea about the efficiency of the readings. And why are they proof? Because maybe you are using a near field communication, inductive coupling. Remember, for LF and HF, it's not sensitive to the metal and liquid. But I'm sure that there is no, it's not UHF. Or if it is UHF, you use plastic for protection. Okay. Okay, very important. There is no doubt. If the enemies of UHF is liquid and metal, so use plastic. I don't know if I can show you. Maybe I can show you. I will bring with me tomorrow. Tomorrow I will show you something about that with plastic, and because we did RFID network with PC computers and laptops and so on. This is metallic, and we put RFID tags on them, and we use UHF. So we use a plastic insert that more than 4 millimeters. So you put plastic, you are sure that you can communicate. Okay, tomorrow I will show you these tags, this type of tags. Okay, I will bring this because we have camera. I can show you with my. Okay, there is a for the metal and also for the water. It's the same experiments and same. Beyond 6 millimeter, we are safe. We have 100% of successful reading. Okay. The portal configuration. Frequently in a warehouse, portal it may happen. This is the portal, okay? And your question, Watara, yes, this is circular. I put four antennas, but maybe in our experiments here, we put here a linear, vertical, linear, horizontal, circular, and we change the angle of the antenna. So we are sure to cover all the space here. So usually and generally speaking, we can use a mix of type of polarization to do that. Especially because when you are in this configuration, which is called portal configuration, and frequently when you are using a multiple number of antennas, it may happen that one or several tags are read in addition to the real tags. So these antennas are connected to the reader. You have cable. Reader and then to the computer. Maybe Wi-Fi connection. Because you have database management, you have smart applications, and you have a track here. You have your palettes with tags. So you can go in or go out. So when you go to this, instantly, few microseconds, you can have maybe 5, you can count maybe object. Yeah, up database, you know that these objects are shipped or are entered your warehouse immediately, real time. So even if you are fast, you can do this reading. Okay. You understand the application, huh? Okay. So, but if you sometimes you can have what we call ghost read, les lectures fantômes. Ghost read. Ghost read. This is due to the fact when you have multiple tags, multiple interferences, the reading you have the real, but maybe you will have the number you have. If you do not configure well your network, you will have this number 62. In reality, you have 15,560, but your reader and your computer, you are reading, you are counting 15,562. Two are ghost reading. Why? Because you have missed an information because of the presence of noise, multiple reflection. There is a reflection, there is a wall here, you are not watching well what is the envelope. So you have just, for example, this request for reading, striking the wall, and then it returned to this antenna, and this antenna, maybe it's not the tag, but it's only a reflection. And so multiple reflection interference can change the number of EPC. The EPC number can just a small bug, and then you have ghost read. So the ghost read is mainly due to the presence of noise, multiple reflections, and interference. How to avoid this? So it's very important to remember the ghost read and the reason of the ghost read. Okay. To improve the efficiency of reading of multiple tags when crossing a portal, we can install multiple antennas at diverse orientation angles. So this is why I told you, Watara. So in order to maximize the reading and the good readings, you can change the angle in order to cover and to avoid interference with the other antenna. Installing multiple with diverse orientation angles, and use antenna having a circular polarization mixed with the other. Okay, the cable length effect. When you are using a long cable, it's not good. Remember the loss. So when you increase your length of the cable, you will increase your loss. So it's very important to use the minimum length of cables, okay, between the antennas and the reader. So it's better to put the reader here, not to take the cable and to go I don't know where, and to put the reader here. It's not recommended. So here you have 1 meter, and here you have maybe 30 meters. This is an error. This is a mistake done by the installators, because they don't know that it costs more, and then you lose your energy. And because when you are and this loss is increased when the transmission frequency increases. So this is very important to remember this. To remember that the signal loss, the attenuation in the cables, increases when the transmission frequency increases when the cable length increases, which is obvious, and decrease if the cable diameter increases. So if you want to minimize your loss, use a multi-fiber cable with big diameter of the conductor. So this will decrease the loss. Okay, so big diameter, short length, and the lowest frequency possible. Yes, because of the impedance, whatever. Yes, in the formula, because when the impedance is lowest when you have a biggest diameter, because the formula between resistance or impedance is this. This is what we call the resistivity. It is specific for the material you are using, copper or so on. L is the length and D is the diameter of the section. So the resistance of a device is inversely proportional to the diameter of the cable of the. So if D increase, the resistance decrease, and which facilitates the transmission. Okay, good, Watara, yes. So you have to remember this because you can have question about that. Using a conveyor. Conveyor, c'est un convoyeur, c'est un tapis roulant. Okay, conveyor. Usually in a warehouse or in industries, we are using conveyors, l'aéroport, par exemple. So the conveyor, you have boxes traveling on the conveyor. So the RFID boxes, yes, conveyor belt, yes. Tapis roulant, conveyor is could be yes. The RFID tagged boxes are sent to a conveyor for shipping. These boxes are randomly positioned. This is a case, a steady case. So in the test, sometimes we give you this question, like a application case or situation case. So these boxes are randomly positioned. What is the best antenna polarization that allows a reading without errors? So I told you earlier that if you do not know the position of your tags, so because it is random here, yes, so the circular is the better. Good, very good. So when you have multiple conveyors, because you can have a big industry, a big company, you have multiple conveyor belts, then you can use multiple sources of RFID method, antennas, readers running in the same time. So what it is recommended to use shields, bouclier, shields, protection are recommended to avoid the saturation of antennas and to use a Faraday cage. I will explain to you. I will try to you have this conveyor, you have box here, and this conveyor will go to different routes. For example, some boxes are tagged, all the boxes are tagged. You have antennas here, and this is connected to the reader. Reader 1. I don't know. I am a poor drawer. Okay, reader 1, and you have antenna here, antenna here, antenna here. Maybe antenna here to confirm. So these boxes, maybe some of them, because you have computer here, and computer with Wi-Fi, for example, and these are connected to the same computer, and your application for example, for this one, B1 should take this route. and B2 should take this route, for example. So the reader read the EPC, yes, and then they select the path, select the path. So because your application here to manage this. But what is happening? You have multiple readers, multiple antennas. Readers are here. Multiple antennas. Readers are here. All connected to the same computer to perform the application. Maybe wired or wireless. And because you have these antennas, you have electromagnetic wave here. You have read zone here. You have multiple conveyor, multiple RFID sources, and it is running this way, running this way, running this way. So this antenna could be saturated by because this antenna will read, and this will read, and because you have many tags, maybe the antenna will be saturated. What we will do, it is recommended to use shields, UHF shields, bouclier. This means that you have a Faraday cage. It's a tunnel, like a tunnel for isolation. So this is isolated, and this is a Faraday cage here, and a Faraday cage here. It's open now. You can, the conveyor is working here. It's like a tunnel box, but with a hole in the middle. Okay, so this will protect. So this antenna cannot read this until the box is here. Cannot read these tags, and this antenna cannot read this because they are protected by this. Okay, this is recommended to avoid saturation and misreadings. Oh, very bad picture. Okay, so is it okay with you? Did you understand the concept of Faraday cage? And okay, when you are using multiple conveyors. Okay, good. Okay. Forklift, chariot elevator. Forklift, you are using vehicle mount readers and computers and antennas. So the best configuration is to install all embedded RFID readers and to send the data wirelessly to the computer. Tag position, it's important. So when you are dealing with a bottle of liquids and metal like this, and you have this box and you have your tags here. So, and you are using UHF because it's long read range, and you have to manage this. So it's very important. Some just little details are important. For example, if you have bottles with the liquid here, it's better to put the tags here, because here you have a void. You have not liquid. Liquid, maybe the bottle are filled until here. Okay. So if you put your tags here, it's okay. Here it's okay, but here it's not good because you are close to the liquid. And same thing for for this can. If you put your tag in the interface, it's better to put them here. Okay, interface, because you are bigger distance to the tag. And this can be managed by the applicator. Remember the role of applicators? The role of applicators is to put the labels, the RFID smart label, in the right place, in the same place, with a good precision of 0.5 millimeter. Yes, Watara, how can we set up UHF shield? It's just a box. There is nothing shield. It's metallic. It's a Faraday cage. It's a dielectric material. There is nothing to. Yes, it's very easy Faraday cage. Just to isolate. Okay. There is no electronics in Faraday cage. You have to ground your system, but so tag positions. Remember, I told you earlier that there is not good. You have to respect the distance between the inlays. Remember, here it's not good because the inlays are very close to each other. And if you have this box, do not put put these boxes close to each other in such a way that you have these tags, okay, in touch. This is better, so you can see the tags are far from each other and are. So it is possible that some tags at the center of the palette cannot be read due to the manufacturer, output power of the reader, distance to the antenna, material in the box. So it is recommended to apply tags as much as possible visible to the outside and avoid overlapping tags. What is the information inside the tag? Now information inside the tag. So all what we said, it's very important for your questions and your knowledge, okay? Now it's very important. Inside the tag, UHF tag, generation 2, EPC global generation 2 standards or norm for the UHF, for the memory inside the chip, there is 4 banks, 4 zones, 4 regions for the memory. We call this region or these zones, we call them banks. Bank 0, 0, bank 0, 1, bank 1, 0, and bank 1, 1. So the bank 1, 1 is empty. This is the user memory. This memory is inside the tag, UHF tag. So in bank 00, you have the reserved memory. Bank 01, you have the EPC memory. And in bank 10, you have the TID memory. And then the user memory. Yes. Yes, I mean, non-volatile, you can, it means that it's here almost all time. You can remove the information here, for example, for user, but it is here. For example, non-volatile, you have a RAM and you have a ROM. You have a RAM, for example, in your computer. If you disconnect the computer, you lost your data. Here you haven't power, so it's correct, but the information you have here are non-volatile. It means that it's still here until you decide to remove this by command. So there is no power on or power off, okay, because the tag is this information is not related to because this information is saved and we communicate this information with the reader when it is needed to be communicated. If you want to change some of these, you can do it. We can change. We cannot change. It is here all the time. All the time it is here. This is why it's not volatile. There is no power on or power off. Okay, you can change it if you want to change it with right here. You can put information. The information can be here for 1 century, for 10 years. You can put this information, and this is the meaning of non-volatile. I put this information here, and it is here. In contrast with, for example, in your laptop, if you are writing something and up you have power off, you will lost your data because you are using the RAM, and the RAM is the data are powered on. No, not virtual or no. So let me explain. Maybe okay. I will draw. This is the tag. Okay, passive tag, UHF passive tag. You have the integrated circuit. You have here, you have memory. Okay, this is memory. Okay, memory. This memory is not powered. Is it here? Your tag is here, and the information is here. You have no power. So you have the APC code, you have everything. When you want to read this information, you have a reader antenna, and then you read this information and you collect this information. Okay. There is non-volatile memory because this information is still here all the time. You want it to be there. Okay. So there is no power on or off that influence the presence of the data here. Okay, and I can change the information here, the user, if I use the reader and a write command. I use write command, and I go there and I change the information, maybe the name of the tag, and then I cancel this information. The tag will be here for 10 years with the information you are entered or you are changed. There is no volatile memory. It will stay there. The difference between volatile and non-volatile. Volatile, it means that there is a device, there is power, and all the time where you have power, you have the data. If you cut the power up, there is void. There is no information at all. Okay, we cannot lose the information once we write it, and we can write multiple times, change the information multiple times. Okay, it's like you have a book, you write something on it, and it is here. It is here all the time. But you can take an eraser and you erase information inside the book, and you write something, and it's still there. But if you are, this is non-volatile. But if you have, for example, a cell phone, you write something and up, you do not save, so it's volatile. You didn't save this information, so it's gone. Yes. Okay, so you have these zones in your tag, and in your tag, bank 00, you will have the kill password and the access passwords. Because these are entered one time, you can save the password to communicate with this tag and the password to kill this tag, to make it unusable for other persons. Okay, but this is in your communication with the computer and the reader and the reader. So in order to communicate with this tag, you can put password, and you can kill this tag if you introduce the right password. Yes, RAM is volatile. Yes, yes, Lisa. Yes. So it's not RAM here. It's not RAM because there is no. It's ROM because but ROM with the writing and possibilities. Okay. So the first bank 00, not read only, Lisa. It's a ROM but not read only. It's write and read. We can write it. Okay. It's non-volatile, but we can write on it. We can change the information, not for everything. For example, this we cannot change. This we cannot change, but this we cannot change. Yes, but by powering this and command from the reader, we can change the information with the reader, with the command reader. By exchanging information, we send the information we want to change, and then we save it here, and we can read it. We can write it, and we can read it. Yes, by the by backscattering, because in an inductive coupling, usually we cannot yes, the ROM is but we can change it, the BIOS or something like that. We can change it. We can have the possibility to change it. It is here, but we can change it. If you have the right to do, you can change it. EPROM, yes, the best the best one is the EPROM, is the best, the closest. Yes, exactly, electrical. Yes. Okay, but it's not. It's different. You have to forget the just focus on the because there is some places you can change and some places you cannot change. You are allowed, because for example the tag identification, you cannot change it, change this information, because it is related to the manufacturer of the tag. It gives the name of the factory and so on, so you cannot change it. The serial number of the tag, and not EPC, the serial number of the user, and this you can change, because the password and the access password it's you who determine the key and the access password, and you save it here, and there is only you who know the password. Then this tag can be accessible only by you, because you know when you exchange information, you will retrieve the password, compare the password you entered, and then if the password match, then you can access to the so this can be changed by the administrator or by you if you are the owner of the tag. So remember, reserved memory, EPC memory, TID memory, user memory. So in the bank 00, you have key and access passwords. In bank 01, you have the it is the redundancy cycling code, which is a code to control the errors. You know this in computing, it's very very common. This is to verify, to check if your communication is right or not. The animal human The protocol control PC is used to manage the communication. Maybe you need to transmit after the EPC product some information here, and the PC control will be the protocol used by the user to transmit additional information besides the EPC. The EPC code, the electronic product code. Remember, this is the EPC we saw earlier for identification and so on, and this is the 96 bits here for the EPC. The tag identification is related to the tag itself, date of manufacturing, name of the factory, the serial number of the tag, not of the product, but of the tag, and then the user memory. Okay, the first bank. So you have 32 bits for the kill password permits to that will allow to kill the tags. Okay, and the access password, 32 bits, and you can lock the reserved memory. Okay, you can lock this. Second bank, EPC. Remember the EPC code. You have the 6-bit for this to check the error detecting code, and you have the control protocol code and the EPC code we saw earlier. The TID manages the tag identification according to the fabricant. So there is the standards used for this tag, the identifier of the tag designer, and the model of the tag, and the manufacturer can include information such as the serial number or other information related to the tag. It's different from EPC. The user memory manages the information that user may enter in this zone here. So there is 3 group of comments for reading the reader tag communications. There is select, inventory, and access. This is the group of comments. So tag can be hacked if we do not set password. Yes, yes, Watara. Yes, and this is the problem. Yeah. So you can use exactly the encryption and the coding with password to be sure that. Okay, so there is 3 operations of the reader comments: the select group of comments, the inventory group of comments, and the access group of comments. For the tag, we have what we are calling states. So the tag could be in a ready state, an arbitrate state, and replay state, an acknowledged state, an open state, and secured state, and killed state. So this is the state of the tag and the group of comments of the reader. So for the select group, you can have these comments: target, action, mask, memory bank, pointer, land, truncate. We can write a script using the target command in order to precisely filter the tags you want to process. This is done by programming, but this is not our goal here to know how to program these actions and so on. You usually have the software that do this for you, and you can program only application layers. Okay. For the inventory group, for the reader, you can have this comment: query, query adjust, query rep, acknowledge, and non-acknowledge. Prepare the inventory group, prepare the request to address to the filter tags. So this is to prepare the request after filtering the tags to which those we will do communication. Yes, yes, there is many API to program. Yes, yes, there is many applications. This is the low-level programming for the readers, and they already have done. When you buy a reader and you have just .NET or C#, you can have a minimum of this application. But only if you are working in this field to design a reader or to work in security of communication, you have to be familiar with that. But it's not in our goal. It's not in our course for this. Okay, just to give you an idea, and it's important to know what is important to know that the reader have 3 group of comments. Select inventory access. The role of each group must be known. The state of tag must be known. Okay. And for the access group, you can read, write, kill, block, write, block, erase, and lock. Okay. This is the group of commands for the reader. The readers should be powered on. So to put the reader at the adequate power, because the reader will provide here there is the connection to the cable to the antenna. Okay, so here I have antenna here. So and you have electromagnetic wave. That is okay. So the legal limit power limit is the legal power. Remember, we saw that for 4 watts or 2 ERP, and so you have the legal limit of the power, but you have to consider the gain of the antenna, because the antenna has a gain. So if you have a gain, you will be, if you power it for 2, maybe you will have 3 with the antenna because of the gain, but you lose power because of the cable. So in order to have the right power to send, the right power is equal to the legal limit of the power. We subtract the gain, because the gain should be subtracted, and we add the loss of the cable in order to have the right power to use for your network. Okay. So imagine you have the right the legal power for what you are with thanks to your gain, you can gain 2 watts. So you have for it means it will be 6, if it will be 6 here, because yeah, so 6. Here you have the limit, the regulating. You have to have 4 here, 4 here. So the limit will be equal to the power. Power could be 6 if you gain 1. So if you gain, for example, 3 and you lose 1, you can, so okay, so it will give you 4. For example, if you have a limit power of 4, you can have the power of your reader equal to 6. You should reduce the gain, which is 3, and you can add the loss, because you lose this in order to have the power, the power here, to respect the power that will be used by the network. I don't know if I am very clear here, but just remember that the legal limit of the power, the antenna gain, and the cable loss. So the cable loss, you lose energy, so you have to add this. You take into account by adding this to your power when you tune the power of the reader, and then you have to reduce your gain you can have for the antenna, and the gain of the antenna is provided by the buyer of the antenna, the company of the antenna. Middleware management of the RFID. So you have a middleware, which is a software that manages your RFID network. So the management of the information collected by the reader, when you have data collected by the reader, integrate information for the company. So depending on what you are doing, shipping, inventory management. So you have two type of middleware. You have the low-level management software and the high-level management software. So for the network, you have the firmware, which is like the operating system of the readers and so on. You have the software which manages the failures, the alarms, and the power. And you have the high-level management. The communication with tags are considered in the high-level management: reading, writing, anti-collision, and data encryption. This is on the reader and the middleware. But you can have application or user applications that are over this. And this is what we call smart management applications. So for the middleware, you have the low-level management, operating system, management of the failures, the alarms, the power, to tune the power. And for the high level, read and write onto the tag, manage the collision of information. When you, just like Wi-Fi, you know that you have collision of the packets, so you can manage the anti-collision. And the data encryption, because you can encrypt your communications exactly like Wi-Fi or communications, radio communications. Dense environment. There is two type of dense environment. There is difficult conditions, adverse conditions. It's not easy conditions for working. So we can have dense reader mode and dense tag mode. Dense reader mode, it means that in an operational environment there is a number of many number of active readers, and more than the available channels. Remember the channels, maybe you in France you have 10 and you have 12 readers. What you can do, you can manage to work in dense reader mode. So to work with this in this situation, you can use shield, reduce the reader power, even if you are using the same channel. So you use a Faraday cage, you reduce the reader power, and you read only when you need. When you need, not reading every time, but to program the reading only when you have the conveyor, for example, working. If the conveyor is not working, you do not perform reading. This will reduce the risk of errors, and you can manage the dense reader mode. Okay, so the dense tag mode is an environment where you have a great number of tags. So you have many tags that are read by multiple antennas. So it happens when more than one tag tries to respond to an interrogator at the same time. So you have many tags. You have a reader, antenna connected to the reader, and then you have, when you have a lot of tags, so there is collision, but not only collision, but you have a communication of more than one tag. So you cannot manage this because you have multiple tags. So dense tag mode, it occurs when more than one tag tries to respond to an interrogator at the same time. So to avoid this, maybe to augment the number of antenna, so this can manage to have an answer with the other antenna. And to add anti-collision configuration. So if I ask you how to deal with dense tag mode, you have to answer this. Augment the number of antenna and or the reader with an anti-collision configuration. Anti-collision is important. To manage the dense reader mode, shields, reduce the reader power, and read only when it is needed. Here there is a new situation, a situations case. A series of new installed tags are not read. So you renew your stuff of tags, and then you notice that there is no readings. What are the recommended actions to do? The actions to do is to upgrade the reader firmware, because certainly the reader, the firmware of the reader, the operating system of the reader is obsolete, so it's not up to date. So you have to upgrade the reader firmware. This is the first thing to do, and use the compatible tags. Maybe you are using a channel that is not adequate. You are in France and you are using the US equipment and so on. So this is the situation. What is the principal advantage of a programmable reader versus a non-programmable reader? There is a different type of readers. So the readers are, you can have a very smart reader with many features, and you can have a reader just to read and to transmit the information, the APC, to the software, to the host system, to the computer. So the programmable reader can manage the traffic. You have less traffic, and because you can filter, you can do command, you can group, you can use select and inventory, you can perform the data filtering. Donc this is why it's advantageous to have a programmable reader. But nowadays it's very rare to have just a dummy reader, very rare. So the anti-collision system in RFID network is very important now, because it allows the reader to interact with a great number of tags and to avoid the dense reader mode, to work in the dense tag mode. So the printer, you have the printer. The main features of the of a printer is the printing speed, the paper feed shift, the tag length and width, the orientation of the tag, the memory configuration, the Wi-Fi, and you can have a system feedback and applicators. It is connected to this system feedback. It's for alarms and so on. The printing, you have two methods for printing in the RFID printing. You have the thermal transfer method and the direct thermal method. The thermal transfer is you have a print head and you apply the heat to a ribbon. The ribbon is here. You apply a heat, and then you have an ink exactly like a printer into the material to form the image. This thermal transfer is the one which is used currently, and it is more resistant.